myself Ansar Rahman. I'm a graduate student here at FES. I'm doing Masters in Applied Mathematics under the supervision of Associate Professor Dr. Naveed Razak Bhatt. Today I'm going to talk about a part of my research here at FES entitled Estimation in Non-Stationary Harmonic Processes with Biomedical Applications. First we have outlines. We'll start with the background of this study, followed by applications, then we'll see the motivation behind the study, and then we'll state the objective. Next, we will have methodology of the proposed work, followed with some experimental results on synthetic signals, and then we will see a biomedical application, electroencephalogram, EEG signals, where we have applied our proposed work. Finally, we'll end with conclusions. So in signal processing, our signal is basically a function that conveys information about a phenomena. Here we have some different type of signals, and we classify signals on the basis of different features. And here we classified signals on the basis of its periodicity. So our concern is with periodic signal. A periodic signal is basically a signal which repeats itself after a certain period, after a certain interval of time. And here we can see some well-known sinusoids, some well-known periodic signals: sinusoid, square wave, ramp function, pulse, and arbitrary function that repeats itself after a certain interval of time. And we can also see a periodic signal here, which we can see that which will not repeat itself. So in periodic signals, we have different type of patterns. We can see a noisy periodic signal here, and in any periodic signal there are certain patterns there. So our concern is with a certain pattern which is harmonicity in between the periodicity and in the periodic signals. So our focus is basically on the harmonic signals. Harmonic signals are basically signals in which there are certain frequencies, and among the frequencies there is some lowest frequency which we call fundamental frequency, known as pitch, which is usually denoted by F0, and there are some higher frequency components usually denoted by Fk, which are called harmonics. And the harmonics are basically the frequency of the harmonics are integer multiple of the frequency of the fundamental frequency. K basically denotes the total number of harmonic components. In this picture we can see that the first we have a certain period and a wave which completes first circle, so first cycle, and in the second harmonic we can see that the wave basically completes two cycles, and here the frequency is the integer multiple of the fundamental. And similarly we can see in the third harmonic and in the fourth harmonic the wave completes 3 and 4 cycles respectively. Here are although harmonic comes from a word music or sound, but besides music, audio and speech signals, we can also see harmonically related signals in some other applications, which includes string instruments also, and some power quality signal analysis. We'll also see this in fault diagnosis in rotating machines. But our concern is here basically on some biomedical applications that includes electrocardiography, and we can see that here we also have periodic signals. But mainly we apply our proposed work on electroencephalogram, which is basically a neuroscience application. So EEG are basically brain signals that tell us about the brain activity. So here's the motivation. Fundamental frequency estimation is a well-known problem in the literature, but most of the estimators that we see in the literature, they assume the stationarity. Here stationary basically means that statistical stationarity, which says us about that the statistical properties are stationary within the signal along the period of time. And however, this may not be the case in some real world scenarios where the fundamental frequency and related harmonics both are often changing with time, such as EEG signals, EEG measurement of seizure as given in the 4. In such non-stationary signal applications, the instantaneous fundamental frequency becomes a parameter of practical importance, and our objective is to estimate the instantaneous fundamental frequency of non-stationary harmonic signals. Here we have a non-stationary harmonic signal coming from a single source described here in 1, where K represents the total number of harmonics, total number of frequency components, and AK of T here is basically the slowly varying amplitude, and F0 of T, which is basically our concern, here represents that instantaneous fundamental frequency. Commonly we say it IF. Assume that this signal is made at n instants and with the suitable sampling frequency Fs. Here are the steps for our proposed work. First, we will find the local energies of the signals, where we locate the time instant where we have the maximum energy of the signals, and then we will apply at that time instant a window, which will be a fractional Fourier window. After applying the window, we get a stationarized signal, and on that stationarized signal, we will find out the model order, the total number of components. The novelty of this estimator is that we are not incorporating we are not giving estimator the total number of components. It is also estimating the total number of components along with the if estimation. So the proposed algorithm, termed here as IFFF, instantaneous fundamental frequency estimator, is implemented as follows. First, as I said, we will find out the time instant where the signal is strongest. That means that the energy will be maximum in that local duration of time. Mathematically speaking, we basically find out the area under the curve in between some small durations in small chunks, and then we will find out where the energy is maximum, and we will locate that. We will say that time instant is t naught hat, and here basically delta represents the window length. 2 delta is the length of the local window to estimate the local energy of the signal. The smaller value of delta improves the estimate of the local energy because we will find out the energies in some small chunks. Then after getting the T naught, where we have a maximum energy, we will apply the window and we will get a window signal. A window here will be a fractional Fourier window described in 4. Here window function, the parameter in the window function is the alpha, that is rotation order of the analysis window, whose range is between -1 to 1. So we also find the optimum rotation order that will give us the compact signal. The compact signal means that we will rotate the signal such that we will get some minimum number of Fourier coefficients in the Fourier series, in the Fourier domain, such that it will also reduce the computational cost and also increase the efficiency. The aim of this step is to stationarize the frequency modulated chips expressed in 5, where x alpha f is basically the Fourier transform of the signal, but within the window. And how do we find the optimum rotation order? We will find the optimum rotation order using a grid search between -1 to 1 with the quantization level L divided by 12 plus 1. We choose L equals to 100, but we can also increase the value of L, but at the expense of additional computational cost. And note that since amplitude was slowly time varying, so within that windowed signal, the amplitude will be assumed as locally stationary. So after getting a windowed signal, the signal will be stationarized, and we can also apply some model order estimators that we will see in the literature. Here we apply maximum a posterior approach expressed in 1. We'll see in the references, and this K will give us the model order. It basically find out the maximum. It basically find out the minimum variance of the residuals expressed in 8. And here WL is basically the window length, and window length depends upon the rate of change of the instantaneous fundamental frequency. If the IF is changing instantaneous fundamental frequency is changing very rapidly, then we will reduce the window length. Otherwise, we can just contain it as the fourth part of the signal. ZK is basically the Van der Mode matrix that contains Fourier vectors, and AK is the complex amplitudes in this 8. And we can also see the matrices here. And Z is basically Z contains the Fourier vectors that will that behave as a basis function for us, and that basically maps, that projects the AK to the domain of to the range space of X. Finally, we will get after getting the optimum model order, we will find out the fundamental frequency using the non-linear least square method given in 9. And here ZK hat is basically the Van der Mode matrix containing K hat columns. In the previous equation, ZK contains basically the columns are we will see the columns as corresponding to the model order candidates, because here we are estimating the model order. But once we get the model order, then we will find out the Van der Mode matrix according to that optimum model order. And after solving this 9, we'll see that this NLS estimator is basically none other than maximum likelihood estimator. So basically, maximum likelihood estimator basically reduces the L2 norm within this 9. We can see that ZK. After solving this, we can get this 10. So this will be our final estimator. So after getting the instantaneous fundamental frequency at T naught, now we will move our window to the right. by incorporating the time to be Tp plus 1 by f of s, where start with T naught, P equals to 0, and fs will be the sampling frequency. Here the optimum rotation order will be estimated, but this time we will narrow our region around the alpha naught, because alpha naught is already optimum rotation order. So we will narrow our region within this search. After getting the window signal, we will again apply the instantaneous fundamental frequency. This time there is no need to find out the model order, because model order is already estimated. So within the whole signal we will get our model order. And to the left we will repeat the same steps, but the time counter will be decrements with tq minus 1 by f of s. We compare the performance of our proposed work with some alternating algorithms, having the sliding window approach that uses just simple Fourier window, and the IF estimation algorithm that uses fractional Fourier window, but here the model order is not the part here. It basically assumes as signal as a general. So in our work we are incorporating you can say constraint harmonicity. So this constraint basically increases the efficiency of the estimator, and we will see how it increases the efficiency. And we can, the signal that we consider here having have 3 components. So signal duration will be between minus 0.5 seconds to 0.5 seconds, and the sampling frequency will be 128 hertz. We can see that this is the signal, this is the realization of this signal, but we cannot see the 3 components presented here, because this will give us the superposition of all 3 components. And if we apply the Fourier domain, or if we plot them individually, we can see that there is a fundamental blue line, and the red and the black one are the harmonics of that, and their frequency is higher than the fundamental. This figure shows us the estimates of from the IFFF, the proposed work, the IF estimation, which uses a fractional Fourier window, and the conventional that uses ordinary Fourier transform with a sliding window. And we can see that this red squares is the true IF. If we know the nature of our true IF beforehand, then we can also apply the polynomial fitting that we did, and we get the smooth curve of our estimates. And we can see that this blue one is far close to the true IF as compared to the black one and the magenta one. Magenta is IF estimation and black is the conventional approach. In this figure we can see the performance of our proposed work along with the other alternating methods. Basically we see the MSE curve, mean square error curves in dB, and we can see that our proposed work, the blue one, gives us a far higher performance as compared to the other ones. This red straight line gives us the Kramer-Rao bound, which is the bound for any unbiased parametric estimator. So our estimator being biased gives us a very high performance. So this figure is for known model order, because the IF estimation model has a constraint, has a restriction, because it will not work if the model order is unknown. It will only work if the model order is known beforehand. So it needs the number of components beforehand to just give the estimates. So when we estimate the model order, then that part will be dropped, because that estimator do not find out the model order. So we have only 2 methods left, conventional method and IFFF method. And conventional method basically uses the sliding window with the ordinary Fourier transform, and IFFF uses the sliding window with the fractional Fourier transform. So we see that this gives us a better performance as compared to the ordinary Fourier transform, because it uses fractional Fourier window that basically rotates the signal. It increases the compactness, gives us the small amount of Fourier coefficients. So here is we can see in this graph the model order comparison between the conventional method and IFFF method. So in the start, when we have 0 dB, they both perform almost same, but when we increase the dB at higher SNRs, our proposed work basically gives us 100% model. It estimates the model order 100% accurately, while the conventional method drops down at high SNRs. So as we said in the biomedical application, so we apply our proposed work at an EEG signal that gives us a seizure activity, where we have harmonically related signals. The accurate estimation of the IFS in such signal is important in automatic detection of seizure activity. So for detection of seizure activity, we need the IF estimate, we need the instantaneous fundamental frequency to detect the seizure activity. So the time frequency representation of the seizure signal is we can see here At this between 1 to 2 in the time frequency representation, the ridge is very strong, which tell us that here we have the strongest component of the frequency. That is basically our fundamental. And we can see that at above it we have two other ridges. That shows us there are three components in total in this signal. In this figure we can see the estimates from IFFF and from other alternating methods. So they we can see that they follow the ridges, the similar ridges as we can see here, but we can see that the estimates are quite close. But then where is our novelty? The novelty is that the IFFF method estimates the model order correctly as compared to the other one, while IF estimation method, being efficient, will not find or will not estimate the model order. The second novelty is that its computational cost is very low as compared to the other methods. So the conclusion: the proposed method basically employs fractional Fourier window to stationarize a signal, followed by map estimation to estimate the model order, and then it estimates the fundamental frequency using non-linear least squares. The effectiveness of the proposed estimator, we saw that both with the synthetic signal and the real-life EEG CG recordings. Experimental results demonstrate that the proposed estimator, while being biased, achieves better performance as compared to the other alternating methods. Here are the references. Thank you.